Hello. Firstly, I wanted to acknowledge my colleagues within PIRSA, so Mel Fraser, Dave Davenport and Dave Woodard, who I have borrowed information from for their projects. Also wanted to say thank you to Tim Herman from Department of Environment and Water for his support. I'd also like to acknowledge our funders for contributions and collaborators, which is Department for Environmental Water, the Goyder Institute, GRDC, SARDI and CSIRO. Now, we are inundated with information these days. You Google soil health, you get 50 million results in less than half a second. You get just about as many different responses for definitions for soil health. And the one I like is a measure of the capacity of a soil to function as a living system. Why is soil health important? Well, we know we have environmental benefits. Our soils are a filter for our nutrients, for pollutants. They are important to stop erosion. There's also a huge economic benefit. Just in South Australia alone, agriculture is one of the largest employment. In last financial year, agriculture generated revenue of over $22.5 billion. But really, soil health is really important because it produces our food. Over 95% of food is grown in association with soil. Now, the FAO have said that by 2050, we need to increase food production by 60% just to supply the increase in population. Now, we know that with an increase in population, we're going to have less land to grow more food. So we need to increase the productivity of our soils. There is a great book released in 2016 by Sterling et al. On soil health and sustainable ag, and I pinched this quote from them. Agriculture will only survive in the long term if soils are managed in ways that not only repair historical damage, but also improve their soil, physical, chemical and biological properties. Now, over 2/3 of Australian agricultural soils are deemed to have one or more soil health limitations. And here is a list of things that you can measure within the soil that generate a soil health idea. There are 3 components. There's the physical, chemical and biological. And unfortunately, as scientists, we often focus on one of these components, or we pick one of the little bits out of there and focus on it. Now, it's critical to understand that there is not one universal benchmark for soil health. A specific definition that you would use in a natural ecosystem is different to one that you would use in an agricultural system. And within an agricultural system, we'll have a different definition for a sandy soil than we will for a clay soil. And that's determined by the soil texture and the way that the soils are formed. These things largely determine the physical, chemical and biological properties of the soil. It's important to know that these 3 pillars, the physical, chemical and biological, need to be in balance to have a healthy soil. And the biological processes are often the bridge that forms between the physical and chemical. Now, there's one thing that links all 3 of these components, and that's organic matter. Organic matter has a critical role in improving soil properties and improving soil health. For the physical component, it's important for air and water movement. For the chemical, it's important as both a source and a storage of nutrients. And of course, we know organic matter is the food to sustain the soil biology. One thing that we need to know in a healthy soil, one that is functioning well, you have organic matter cycling all the time. High capacity, high functioning soils turn over organic matter. And in that way, you may not get a carbon sequestration benefit from some of these highly healthy soils. So how do we change? One thing I forgot to say, organic carbon is often spoken about. Just remember that organic carbon is a measure of organic matter. Organic matter is so much more than just organic carbon. So how do we change this theory that we now know into something that's practical and applicable in our state's policies? So following the National Soil Carbon and Land Research Program, Department of Environmental Water commissioned a report in 2013 that assessed the soil carbon status of our agricultural soils in South Australia. Now, we're incredibly lucky in South Australia to have such wonderful mapping of our agricultural soils. There is information available. One really good item is the soils of South Australia. And the second we have is a fantastic database that encapsulates all the information from the soil mapping. And that's called the State Land and Soil Information Framework. Now, this report utilised the framework and analysed over 1,100 characterisation sites. And it managed to identify the soils with the greatest potential to increase carbon stocks. Now, these soils were the sand over clay, so the G soil group, the deep sands, the H group, and texture contrast with brown or dark subsoil, so the F group. These soils were deemed to be able to modify a soil constraint. The next three soils that had high potential, the ironstone soils, and soils that have either as an acidic, highly acidic, or highly alkaline subsoil, even though they had a high potential, there was an opportunity to increase carbon in them, it was deemed to be uneconomic or impractical to overcome the constraint. So we're focusing on those first three soils. So with funding last year from Department of Environmental Water and the Goyder Institute, we collated all the information, the soil carbon information, on sandy soils, so those G and H group soils, that have had subsoil clay added to them. You can see by the diagram down below that the clay is added in clods, and this is through clay spreading or delving. And the fantastic news is we can say that we can definitely increase carbon stocks in these soils. We also know that in different rainfall zones, there are different factors that impact on it. So we're happy. If we were measuring soil health as a carbon benefit, and even a wind erosion benefit because these soils are more stable, we can say that application of clay to these sandy soils worked. However, if we were measuring productivity, we flick over to the New Horizons program, which is now part of the GRDC Sandy Soils, and that's led by Mel Fraser and Dave Davenport. This was a research trial established in 2014, where they were looking at, again, on these sandy soils, deeply incorporating clay, organic matter, and the deep placement of nutrients. They had 3 different sites, and if you look at the 3 different sites there, out of 2 of those 3 sites, the incorporation of clay didn't result in the greatest productivity. So if we had soil health measured as productivity, we may not consider clay in that. However, if you look there, you get 3 ticks for organic matter. If you deeply incorporate organic matter, productivity was fantastic. But then if you look at the economics of doing that, it wasn't feasible. It wasn't economic. They are now looking at research options to incorporate organic matter with different products or at a lesser rate. We flip over to those F group soils. So these are heavier soils. Normally, a lot of them with the red-brown earths in the mid-north. So Dave Woodard set up a number of trials in 2014 and 15, where he actually had deep placement of products, so amelioration products, which could be anything from gypsum to biochar to chicken manure. And he actually placed this product deep into the area where the subsoil limitation was occurring. So that could be anywhere between 20 and 40 centimetres in the soil. Now, this happened over a number of 6 to 8 sites, and Dave Davenport is now continuing this work in a GRDC research trial, subsoil trial. You see there's the graphs of productivity again, so we're measuring this by grain output. At the top site, fantastic. We've got great responses, different products, fantastic. But the second property there wasn't a change. So the biggest outcome that we had, key learnings from the science, is that you need to match your modification practice with the greatest subsoil constraint that you have. It's really horses for courses. You need to be able to understand your soil. When we're talking about health checks for sustainable agricultural soils, We need to keep in mind that these are people's livelihoods. We are talking about farms where people need to have a livelihood, economic sustainability and viability into the long term. So what needs to happen is you need to define what soil health is for that situation based on economic, productivity and soil goals. You need to be able to identify the soil type and the limitations in that profile. And then you really have to understand which of those limitations can be changed and what can't. You then have to modify either your expectation of your soil, you modify your management practice, or you modify the soil itself to be able to gain what you need to. And then you have to monitor key soil, plant and economic attributes to measure the soil health, and this is linked back up to your goal that you set. And of course you need to reassess your system and you need to know it's working. And just be aware, and whenever we work with soil, there's complex interaction goes on. It can take up to 3 to 5 years to see some changes in any properties. So we need to have patience when we are looking at changing soil health. That's it.